Before we talk about electrical temperature sensors, let's first understand how non-electrical thermometers work. One of the most common examples is a mercury in a thin glass tube. When the temperature increases, the mercury expands. Because the tube is very narrow, the mercury can only move up the tube. So as the mercury rises, we can read the temperature directly from the scale. The key idea is that materials expand when the temperature increases and contract when the temperature goes down. This is a purely physical measurement. No electricity is involved. Electrical temperature sensors work in a similar way, but instead of measuring expansion, they measure how electrical properties change with the temperature, such as resistance and voltage. There are three main types of electrical temperature sensors: RTDs, thermocouples, and thermistors. We will explain each one in some detail. RTD stands for Resistance Temperature Detector. An RTD measures temperature by using the fact that electrical resistance of a metal changes with temperature. As the temperature goes up, the resistance also goes up. This happens because the atoms in the metal vibrate more, so electrons have a harder time moving. That makes the resistance go up. Most RTDs are made of platinum. A very common RTD is called the PT100. That means its resistance is 100 ohms at 0 degrees Celsius. Between 0 and 100 degrees Celsius, the change in resistance is almost linear, which makes RTDs easy to use as you don't need to do complicated math to get temperature. The resistance changes by about 0.385 ohms for every 1 degree Celsius. For example, if we measure the resistance on the RTD to be 110 ohms, we can estimate the temperature like this. Temperature equals 110, which is the resistance that we read, minus 100, which is the base resistance at 0 degrees Celsius, to divide by 0.385, which is the coefficient of change. That gives about 26 degrees Celsius. So the main idea is that if we can measure the resistance of the RTD, we can estimate temperature. RTDs are very popular because they are accurate, stable, and nearly linear over a useful range. They can measure between minus 200 to 800 degrees Celsius. Okay, so let's demonstrate how an RTD works. So as we said, when you heat up a metal, as the temperature goes up, the resistance goes up too. So here we have just a metal, which is room temperature. You can see it's around 1.7 ohms. Let's heat it up and see, as temperature goes up, resistance will go up too. Right, so you see we're just heating it with fire, and wow, the resistance is going up. So if we know its coefficient, we know how much the resistance goes up for every degree Celsius, we could measure temperature. The thermistor is another type of electrical temperature sensor. Unlike an RTD, a thermistor is usually made from a ceramic material. Most thermistors are NTC thermistors. NTC stands for negative temperature coefficient. That means when the temperature goes up, the resistance goes down. This is the opposite of an RTD, where the resistance goes up as temperature goes up. Another important point is that thermistors are non-linear. That means the resistance does not change in a straight line with temperature. Instead, it changes in a curve. Because of that, we usually cannot use a simple equation like we did with the RTD. Instead, we often use a Steinhart-Hart equation or a lookup table to convert resistance into temperature. Now, if we don't have a lookup table and we're using the Steinhart-Hart equation and we sample many times a second, it could take a lot of juice from the microcontroller to calculate each time using this complicated equation. That's why if you have sufficient memory, it is much faster to use a lookup table. A big advantage of a thermistor is that they have a large resistance change for a small temperature change, so they are very sensitive. We will demonstrate this soon in the example. Thermistors typically work over a range of about -50 to 200 degrees Celsius. As you can see, this is much more limited than the RTD, which could get into the 800 degrees Celsius, and thermocouples, which could get well into the 2000s. Their accuracy, but is pretty accurate, between 0.1 to 0.2 degrees Celsius. Thermistors are often used in mobile phone, desktop computers, laptop, LCDs, and thermostats. A thermocouple measures temperature in a different way than an RTD. The thermocouple is just two different metals wired together at one end. When that joint is heated, a voltage appears at the other end. This is called the Seebeck effect. The Seebeck effect means that when two different metals are joined together and that joint is heated, they create a small voltage. This happens because the electrons in two metals respond to heat differently. One metal pushes the electrons a little bit more than the other, and that creates a voltage that we can measure. That small voltage tells us temperature, because for every temperature, the voltage will be different. There are different thermocouple types because there are different pairs of metal alloys. The standard types include J, K, T, E, B, C, R, S, and N, but K is by far the most common. One big advantage of thermocouples is that they can measure a very wide temperature range, from -200 to 1800 degrees Celsius, and some could even go much higher than that. A limitation of thermocouples is that they are not as accurate as some other sensors. They are typically accurate at around 1% of the reading. So if we're reading 1800 degrees, they could be off by 18 degrees Celsius, which is a lot. But we need them because other sensors cannot get to these high temperatures. So even though thermocouples are not the most accurate temperature sensors, they are very useful because they are simply fast and can measure very high temperatures. Also, their response is not perfectly linear, especially over large temperature ranges. So engineers often use a lookup table or calibration curve to convert voltage into temperature. Okay, so let's demonstrate the thermocouple. So as you can see, I connected two different types of metals. They have a hot joint, so you can see kind of where they're wrapped around. One is copper and one's a different metal, which I had. You could see there's around, it's pretty close to 0 millivolts that it's detecting. Let's heat it up and we'll see how the voltage kind of rises. So let's do that. Isn't that amazing? So we understand that RTDs and thermistors work by the fact that a change in temperature causes a change in resistance. But there's a little bit of a problem because these thermistors and RTDs are usually connected to some type of microcontroller or computer. Now, these computers, these microcontrollers, they use analog to digital converters to turn voltage into digital numbers. So they work by observing what voltage comes into them, and whatever voltage comes into them, they could turn into a digital value. They cannot detect resistance. So how do we turn the change in resistance that we get from an RTD or thermistor into a change in voltage, which an ADC, an analog to digital converter, could pick up? And a very common solution for this is to use a voltage divider. So what is a voltage divider? So this I want to explain as it's a very, very, very common circuit in many, many types of electronics. So to understand what a voltage divider is, you have to understand two fundamental rules in electronics. The first rule is this. Anytime current flows through a resistor, there will be a voltage drop across that resistor. Okay, if you know from Ohm's law, voltage equals current time resistance. Okay, so always, if we have current going through a resistor, okay, there will always be a voltage drop.
Okay. Second, the total voltage drop in a circuit must add up to the source voltage. Okay, so let's give an example. Let's say we have a battery here. Okay, let's say that battery is 10 volts. Okay, now current flows like this through resistor 1 to resistor 2 and back to the negative. Now, throughout this circuit, there has to be a 10-volt drop. Has to be. Okay? Through resistor 1 and resistor 2, there has to be a 10-volt drop. Now, the question is, okay, but how much drops through resistor 1 and how much drops through resistor 2? Well, the rule goes like this. If resistor 1 and resistor 2 are the same value, and that doesn't matter what that value is, it could be 100 ohms, it could be 500 ohms, it could be 326 ohms. But if resistor 1 and resistor 2 have the same value, then the voltage drop will be even. Okay, for example, let's say resistor 1 is 500 ohms. Okay, so let's do 500 ohms. And resistor 2 is 500 ohms. Okay, so they're the same. Okay, and over here, of course, we have 10 volts. Okay, now, because resistor 1 and resistor 2 are the same value, then the voltage drop will be even. So if here we have 10 volts, resistor 1 will lose for us 5 volts. Okay, so that would be negative 5. Okay, and resistor 2 will also have a negative 5, which adds up to 10, which is what we want. What's important here is that if we check what's the voltage in the midpoint, what's the voltage between resistor 1 and resistor 2? Okay, so if we put our red probe over here, we'll see that it's 5 volts. Okay, why is that? Because we had 10 volts, resistor 1 took down 5, we're left with 5. Now resistor 2 will take down the last 5 and turn it into 0 volts over here. Okay, but in the midpoint, it would be 5 volts. Okay, now let's say resistor 1 and resistor 2 are not the same. So let me erase here. Let's say resistor 1 was, say, 400 ohms, and resistor 2 is 600. Okay, now resistor 1 and resistor 2 are not the same. Okay, how much of a voltage drop will be across each one? Well, resistor 1 is 40% of the total resistance, right? So there'll be a 40% of the sum of the voltage that needs to be dropped will drop across resistor 1. In our case, we have 10 volts, so 40% of that is negative 4 volts. Okay, negative 4 volts. Again, here we have 10 volts we're starting with. We'll have negative 4. So if we measure over here, we have 10 minus 4, this will leave us with 6 volts in the midpoint. Then, of course, the last 6 will be dropped across the 600 ohm resistor, which is resistor 2. And, okay, so let's just say it would be a negative 6 volts across resistor 2. Okay, now the math to do this is this. Okay, let me just move it in. Is V out, which is the voltage at the midpoint, equals V in. In our case, it's 10 volts times resistor 2 to divide by resistor 1 plus resistor 2. So in our case, resistor 2 is 600, right? So it would, and resistor 1 plus resistor 2 is 1,000. So it would be 600 to divide by 1,000, which would give us 0.6 times Vn, which is times 10, which gives us 6 volts. Okay, let me just open here a calculator so I can show everyone. Okay, so we would have 600 to divide by 1,000 times 10, which equals 6. And that's how we could check in any voltage or any resistance, we could check what the voltage is or will be at the midpoint. Okay, so let's put that down. For another example, let's say that Vin is 5 volts. Okay, and let's say resistor 1 is 950 ohms. 950. And resistor 2 is 465. Okay, if you would plug these numbers into the equation I just showed, you would see that over here we should get a voltage of 1.64 volts. 1.64 volts.
I built here a simple voltage divider to demonstrate how it works. So I've connected in series resistor 1 and resistor 2. Both of them are the same resistance, so both are 2000 ohms. Now let's see how much voltage we're getting from the Arduino to determine what we should get in the middle, and then see what we actually get in the middle. Okay, so let's see the voltage across. Should be 5, but oh, okay, 4.88, okay? So if the resistance is the same, we should get half of that. So let's do the math. 4.88 divided by 2, we should get 2.44, 2.45. Let's see what we actually get. Okay, not bad. These are very cheap resistors from AliExpress, but we still see that we get 2.45 in the middle. Okay, now let's change around the resistance a little bit, calculate, and see what we actually get. So I'm going to take out for resistor 2, I'm going to take out the 2000 ohm resistor, and I'm going to put in a 3000 ohm resistor, 3.3 thousand ohm resistor. Okay, now let's do the math. So we have for resistor, so we have 3.3 plus 2, okay, and then we have 3.3 to divide by that, okay, times 4.85, okay, 3 volts plus or minus. So let's see what we actually get. Amazing. You can see we get 3 volts. So you just do the math and you can see it's pretty accurate.
Let's see how we could use it in our circuit to turn the change in resistance of the thermistor or RTD into change of voltage which the microcontroller could understand. So let's say, for example, we have a thermistor which has a base resistance of 10,000 ohms. Okay, 10,000 ohms are room temperature, which is 25 degrees Celsius. Okay, so this thermistor is 10,000 ohms. We would put a fixed resistor of also 10,000 ohms. Okay, okay. Let's say now the voltage is 10 volts. Okay. So from what we saw earlier, the 10 volts will be divided equally between the fixed resistor and the thermistor as they are equal. So the microcontroller will sense 5 volts. Okay, that we know already. Now let's think what would happen if the thermistor heats up. Okay, so now it's at 25 degrees Celsius, but let's say it heats up, okay? And we know that a thermistor, when it heats up, the resistance goes down, okay? So instead of being 10,000 ohms, let's say it goes down to 9,000 ohms, okay? 1, 2, 3, okay? Now, what will the voltage be at the midpoint, okay? So let's do the math. Let's take out a calculator. So we have resistor 2, which is 9,000, right? To divide by resistor 1 plus resistor 2, which is 19,000. Okay, equals, okay, and then we do times 10 equals 4.7. So the voltage will be not 5 volts, right? Rather 4.7 volts. 7 volts. So the microcontroller will sense, hey, it's 4.7 volts. It has to be that the thermistor's temperature went up. That's why the resistance went down, right? That's why also the voltage went down. And once we have the resistance, we could plug in the Steinhart-Hart equation and we could get temperature. Okay, so this is, again, it's just a way to turn a change in resistance into a change in voltage, which the microcontroller could understand. Okay, let's give another example. Let's say instead of the temperature going up, the temperature goes down. So again, here we have 10 volts, okay, and the thermistor was 10,000, but the temperature went down, so the resistance went up. Okay, so let's say now the resistance is 11,000. Okay, and the fixed resistance is always 10,000. 1, 2, 3. Okay, so now let's plug in the numbers. We have resistance 2, which is 11,000, to divide by resistance 1 plus resistance 2, which is 21,000, equals, and then we do multiply that by our voltage in, which is 10 volts, and we get 5.2. So now the midpoint, or the point that the microcontroller, the ADC, sees is 5 volts. 5.2 volts. Sorry about that. 5.2 volts. So the microcontroller says, hey, it's 5.2 volts. It has to be that the thermistor's temperature went down below 25. Okay, and that's why the resistance went up. So again, this is just the basic circuit to show how we could turn a change of resistance into a change of voltage. Now, there is a big problem with this. And the problem with this is that this circuit only works if the source voltage is completely accurate. So let's say there's no fluctuation. So let's say this is 10 volts and it's a steady 10 volts. In that case, we know, hey, if this is, 100 ohm and this is 100 ohm, then this will for sure be 5 volts, okay, here in the middle. But the problem is that what would be if, for example, the voltage goes down for a few seconds to 9.5 volts? Okay, so instead of being 10, it goes down to 9.5 volts. Now, what would be the voltage in the middle? Well, it would be 9.5, 9.5 to divide by 2, as the resistance are the same, it would be 4.75, right? So 4.75 volts in the middle. Now, did the resistance change? No, it did not. Just the voltage changed. So the voltage changed, and we know that it splits in half in the middle, so the voltage goes down to 4.75. But the microcontroller does not know that. It thinks it's still at 10. So it says, hey, it's at 4.75. It has to be that the resistance went down of the thermistor, so it has to be that the temperature went up. So it shows that there was a change in temperature, even though that did not happen. There was no change in temperature. They're both 100 ohms still, or both 10,000 ohms, or whatever it is. Just the electricity flow, the electricity source voltage is just fluctuates and is not accurate. So the voltage divider is a very nice concept, but it has a huge limitation. Unless you have an extremely stable, with no noise voltage source, which will work fine. But if you don't have that, and even there's small fluctuations, the microcontroller will say, hey, there's a change of voltage in the middle, so it has to be there was a change of resistance in the thermistor, and it will give an inaccurate temperature reading. So in the next section, I will show a much more practical circuit that we actually use to measure thermistors, which doesn't have the limitation of the input voltage changing. Okay, so this is a final circuit that we could use that doesn't have the limitations of a regular voltage divider. Okay, so let's see what is going on. So similar to the voltage divider, we have the thermistor, which is 10K at room temperature, and a resistor 1, which is a constant 10 kiloohms of resistance. But instead of just measuring the midpoint, we do two measurements. So let's see what we do. We start off by measuring the voltage across resistor 1. Okay, so We measure the resistance, the voltage across resistor 1. Once we get that value, we could plug it in to Ohm's law, okay, to get current, which is the I, equals voltage, which we just measured, to divide by resistance. Resistance is 10,000, right? How do we know it's 10,000? Because it doesn't change, right? It's a constant resistor. It's constant 10,000. That will give us current. Now, we know that in a circuit that's in series, not in parallel, but in series, current will be the same throughout the whole circuit. Okay, so if here we were able to get a current using Ohm's law, then we know that we will have the same current across the thermistor too. Okay, step 2 is we check the voltage across the thermistor. Okay, once we have the voltage across the thermistor, we plug it in to Ohm's law again, and we get resistance equals voltage, which we just checked, to divide by current, which we got from the first check, right, which will give us resistance. Now, the beauty about this equation, about this method, is that we don't have to give a whoop what the source voltage is and if it changes because we determine the voltage and the current by doing two separate checks. So the voltage could change, and then our checks here will change, and the values will change. So we don't have that problem of changing source voltage.
So as you can see, this is the final product that I've built from a thermistor. So you can see the thermistor is here, and it's connected in the manner that I've shown on the diagram. Just here it's a little bit messy with all the wires. And the output that the computer calculated using the Steinhardt equation goes onto an LCD screen. So you can see now it's around 19.5 Celsius.